Good afternoon. Today we have four wonderful student prize winners. First in line, it gives me great pleasure to introduce Geoffrey von Maltzahn, the 2009 Lemelson-MIT Student Prize winner for his work in the area of cancer therapy. Geoff recently finished his PhD research in medical engineering and medical physics from the Harvard-MIT Division of Health Sciences and Technology. Geoff's inventive spirit began during his childhood when he had sought to improve his home surroundings. As a child, he constructed a system of strings and pulleys to remotely control the lights around his room. He later upgraded his system in high school to enable him to control his electronics via his telephone. As a student at Thomas Jefferson High School in Virginia, a continuing Inventeam school, Geoff's interest in science and engineering first emerged. He later went on to MIT and earned an undergraduate degree in chemical engineering. One thing you'll notice about Geoff is that he always carries a journal with him to record his observations, ideas, and insights into the world around him, which further feeds into his creativity. Geoff's had a lifelong passion with art and continues to paint and draw in pastels. Geoff is the co-founder of two companies, Nanoparts and Resonance Therapeutics. Over the next few months, Geoff will be finishing his clinical rotations, building his two companies, and exploring new opportunities. And in case you might notice that he's quite tanned in a month where it's been very cloudy in Boston, he spent the last month touring and hiking across Southeast Asia. Geoff von Maltzahn.
Thanks, Ed. Well, thanks very much, Ed. And it's wonderful to see Dr. Lemelson here. And thanks to everyone here and to the Lemelson-MIT folks. Today I'm going to talk to you about one of the technologies I developed over the past few years. And these are nanoparticles that communicate with one another to find and treat cancers. And so I wanted to start with some of the numbers surrounding cancer that really motivated me and inspired me to get interested in this problem in the first place. In 2002, cancer killed more than 7 million people worldwide, and that's more than AIDS, malaria, and tuberculosis combined. And in a little over a decade, there's projected to be 15 million new cases of cancer per year. And nearly 70% of these are going to be in the developing world. So what's been commonly thought of as a first world disease is rapidly becoming a global concern. And combating this is going to take behavioral changes, it's going to take political initiatives, and it's also going to take new technologies. In the realm of technologies, I'm going to be talking to you a little bit about cancer therapy. And the mainstay treatments for inoperable tumors have remained surprisingly static over the past 20 years, and they're a combination of radiation and chemotherapeutics, and these are both very toxic, both to cancer cells and to normal cells. And a simple observation that inspired me as to the role that an engineer might play in trying to improve our current paradigm of cancer therapies was that if you examine where drugs go that patients take to treat their cancers, often over 99% of them don't actually accumulate in their tumors. They go elsewhere, and they cause toxicity in those organs. And that's why patients get extremely sick, and their hair falls out, and they often can't work and care for their families. And yet, from an engineering perspective, this is inspiring, because if we could solve this transport problem and develop an armamentarium of therapeutics that could focalize to sites of disease and sites of cancer formation, then without developing a single new cancer drug, we could transform our ability to treat this disease. And so this got me interested in this problem, and specifically the role that nanotechnologies might play and might be able to impact both cancer imaging and cancer therapy. And that's because of some of the unique properties that nanotechnologies have. They can be very bright and multicolored, as you see on the left. They can have magnetic properties that enable you to three-dimensionally image them in an MRI. Or they can have therapeutic properties, either intrinsic to their material or imparted by drugs that they hold within their interior and try to chaperone to a site of disease. And particularly, this last category got me really interested in this area. And I found that people had been doing research in this for 30 years. And rather than get discouraged that people had come before me and it wasn't a new idea, I really wanted to dig up as many numbers as I could find to really ask the question, well, how good have we become as a field at taking medicines, putting them inside a nanoparticle, and getting it go specifically to the cancer that we're interested in? And this is something I encourage all of you to do, and the last team did very well, which is when you enter a space that's unfamiliar, get as many numbers as you can. And I think in this case, it's really revealing. So what I'm plotting here is as much data as I could find in the literature, splayed across an arbitrary x-axis. And the numbers are percent injected dose per gram of tumor tissue. So percent injected dose, how much of the stuff that you injected is present per gram of a tumor. So let's mentally convert this to something that's intuitive to us that we can understand. Just percent injected dose. So how much of what we inject into the bloodstream of a mouse is actually able to go to the tumor in that mouse and not elsewhere? Well, tumors in mice typically weigh about 0.1 grams or 0.05 grams. So you need to factor all of these numbers down by a factor of 10 or possibly 20. So what that means is 30 years into the endeavor to target nanoparticles specifically to sites of tumor formation, on our best day, maybe 2% of what we inject in the bloodstream of a mouse is actually able to find that tumor. And so this means we still have a really long way to go. And it may also mean that we should consider new approaches. And if we're considering new approaches and looking for inspiration, a wonderful place to look is in biology. So over and over again, biology, our bodies have had to evolve systems that are sophisticated and which can rapidly solve complex targeting and transport problems. And what I'm showing here is the process of blood coagulation. So these shapes are platelets, which are cells that circulate in your blood all the time. And everybody's familiar with the phenomena of when you get an injury, you fall down, you disrupt your blood vessels. Within seconds, your body rebuilds essentially an entirely new tissue at that site to staunch blood flow and repair the injury. And so a very simple question is, well, why can't we target tumors with the same efficiency that this system in our bodies is able to repair our injuries? Well, one reason we can't do it yet is that we don't really understand completely how this system works. It's immensely complex. It has hundreds of reactions to it. It involves cells, proteins, small molecules, et cetera. And in the words of Richard Feynman, we can't build what we don't understand. So I think this merits deeper understanding of systems like these. But what we can do is take a very simple lesson from how this system operates and try to apply that to our problem of tumor targeting. And one of those lessons would be that the function in this system occurs at a system scale, and it emerges through communication between multiple components. So these cells, their job is to circulate, and when they sense an injury, instead of just sticking there, they stick there and they try to recruit every single one of their friends that's floating by to stick there as well. They communicate. And it's similar to the proteins that are involved in this system as well. And right now, we don't have therapeutics that can perform functions like communication, so that the 1% that perform that really hard task of finding the tumor in the mouse can actually communicate with the others and help them find out where the tumor is as well. So I set out to build the first system of nanoparticles that might be able to communicate in some sense analogously to this system. And so simply dividing the tasks, I decided to make a signaling nanoparticle and a receiving nanoparticle. So one nanoparticle would do the talking, one nanoparticle would do the listening. The signaling nanoparticle's job is to get there first, that 1% that gets to the tumor. Instead of trying to directly treat that tumor, their responsibility would be to broadcast the tumor's location to receiving particles that are still in circulation. And so I've exaggerated in this picture so you can see the nanoparticles. But the real challenge is that the distance between these two particles is thousands of times the individual nanoparticle size. And so how can you get two things to communicate over very long distances and expect that message to robustly get from one place to the other? Well, an example from our everyday life is cell phones. So one of the key enabling technologies in the emergence of radio technologies and cell phone technologies subsequently was the development of amplifiers, RF amplifiers and electronic amplifiers, so that the very minute electrical signal that the microphone emits, caused by the sound waves emitted from your mouth, can be broadcast locally to a base station and then broadcast out into space so that I can communicate with anyone anywhere in the world. Well, maybe we could apply an amplifier to our problem of getting nanoparticles to talk to each other over very long distances. And so what does an amplifier look like on the scale of biology? Well, actually, the initial system that I first told you inspired this contains many amplifiers. So blood coagulation is a system where the majority of the components are circulating in your blood all the time, looking for inputs associated with injury or not, saying, is this an injury? Yes, no. And what if we could access that amplifier and exploit it to try to transmit messages between two nanoparticles? So something like blood coagulation that has been evolved to robustly perform this function of repairing wounds, we might trick into sending messages between our two particles while also having it perform the function that it's always used to doing, which is scavenging the blood vessels for signs of injury. And so this is what I set out to do, and specifically to build a system where our first category of particles would target the tumors initially, and their job would be to injure the tumor, engage the coagulation cascade, and then a receiving particle would receive all of that abundant local activation of coagulation as a message of, I found the tumor, here it is. So these guys are listening. The message is in the form of coagulation, and it's transmitted by particles that get to the tumor and injure it. So the way these first particles work is they're made entirely of gold, and their job is to injure the tumor. And we were asking, how could we get nanoparticles to actually perform this task? And the way that these do is gold is a terrific conductor, and the electrons are very mobile, and that occurs in nanoparticles as well. And as you change the shape of these particles, you can change the frequencies that those electrons resonate in. So just like different shapes and geometries of bells have different sounds, a rod nanoparticle has a different resonance. It happens to be in electromagnetic form. But this allows these particles to absorb a type of energy that passes through our tissues relatively well. And so what these particles do is they potently absorb a type of energy that is able to penetrate deep into our tissues, and they convert it into heat. So these particles target the tumor. They convert this external energy into heat. That heat causes local injury. Local injury sends this message in coagulation to receiving particles. And I'm going to show you a little bit of data to support the functioning of this system. So both of these are mice. The difference between these mice is the mouse on the left received signaling nanoparticles 3 days prior. Those particles circulated in the bloodstream, and they were able to target the tumor. The mouse on the right did not. A day before we took this image, we injected into the bloodstream receiving nanoparticles, one of which are colored green, one population of which is colored red. The green ones can listen to coagulation, the red ones can't. And so what you see here is a tumor that's growing on the back of this mouse that's been infiltrated with green nanoparticles. So this system of communicating nanoparticles, which is functional on the left and non-functional on the right, is able to dramatically improve the ability of these nanoparticles to find the tumor. And if we quantify this with nanoparticles that are loaded with drug, we can deliver over 40-fold higher doses of drugs in a targeted fashion to these tumors compared with non-communicating controls. And this bears out to a therapeutic result that's durable over time and is able to extend the lifespan of these mice. So this is the relative tumor volume over time. In the cases where we administer non-communicating nanoparticles that are loaded with drug, we see no effect on tumor growth. Free drug alone at these same concentrations gives us no effect on tumor growth, but our communicating nanoparticles are able to repress tumor growth and extend the lifespan of these mice. And so I wanted to talk just briefly about commercialization. This is something I've had an interest in part through my development of technologies. I've realized that there are commercial needs that don't become satisfied, and clinical needs that aren't satisfied unless you develop technologies in such a way that they can actually be translated into the market that you're interested in. And in some cases, that requires active attention to the process of commercialization. And so I founded 2 companies. In my endeavors to build systems of nanoparticles, I realized that I needed really good nanoparticles to build from, and there really weren't good nanoparticles available commercially. And so I saw an opportunity to try to assist research worldwide by taking formulations of nanoparticles that had been patented elsewhere, acquiring them and establishing them into an entity. So we make gold nanoparticles of all shapes for a variety of different applications. And the most recent company, which is really just trying to take off the ground right now, seeks to apply these communicating nanoparticles to the clinical problem of improving drug delivery to cancer. And so in the spirit of this week, I also wanted to end with a design challenge to all of you, and that is, we like to think of dinosaurs as a relatively unadaptable set of species. I mean, they're not here now, so they must not have been able to adapt. But dinosaurs were actually on this earth for over 100 million years. And depending on when you pinpoint the emergence of human intelligence, it's closer to about 100,000 years ago. And so what I sort of view as the ultimate engineering challenge, and a timescale we don't often think over, but which I think that all of you will have the opportunity to, is to think, what do we need to do from an engineering perspective? What do we need to invent so that humans are living on the Earth 100 million years from now with a lifestyle that we would choose for ourselves and with a planet that we would choose for ourselves, et cetera. So I'd like to leave you with that thought. And thank you very much for your attention. And of course to the Lemelson Foundation for everything that they do to inspire innovation here around the country. Thank you very much.
Be needed in order to ensure that your target, your correct target, is getting the coagulation needed, in order to ensure communication between nanoparticles?
That's a great question. So the question is, we're using coagulation, and so how do we ensure that we appropriately induce that in the tumor effectively? So actually, I showed you one way that we do that with a nanoparticle. This requires this external signal, which has some attenuation in normal tissue, so you wouldn't necessarily apply that to a stage of very disseminated cancer because you'd need to get that external input to all of those cancer nodules. There's another system that we've recently developed that depends on a protein that's specifically able to, without any external signals, sense for receptors that are specific to tumor formation, and in the presence of them, induce coagulation in that site. So that's a system where you inject both components, and it completely by itself is able to sense tumors, engage the coagulation cascade, force it to respond to a tissue in a way that it otherwise wouldn't as a means of recruiting therapeutics to that site. Yeah?
One more question. If you have, you said that the nanoparticles respond to any coagulation in the bloodstream. What if they have, say, a blood disease where they're unable to have, their blood does not coagulate very well, or there's another coagulation, blood coagulation in the bloodstream?
That's a great question. So our system, the question is, what if there's coagulation elsewhere? Or what if a patient has their coagulation machinery impaired so that they can't effectively transmit the signal? And it's true that the communication that we're expecting to take place is disrupted in disorders like hemophilia. And cancer patients can be hypercoagulable. So in these mice in particular, even in late-stage tumors, we've seen that we inject, the mice run around their cage like they normally would. They encounter everyday activity, and we see very high specificity for the tumor. And in some ways, that was surprising because we weren't really certain what the background in coagulation targeting might be. So I think that's really encouraging. But there's a lot that remains to be tested in exactly that area.
So this was, this was really interesting work. If I read your graph properly, I'm at a bad angle. It looked like you were suppressing tumor growth, but not reducing tumor size in the mouse data. Is that correct?
The tumor size does decrease.
But it didn't look like it. It looked as a tumor volume, and it stayed pretty flat. If not, it kind of went slowly up.
It does slowly go up over time. So this is at a dose that's completely ineffective without this technique. And we've just started testing higher doses and see increasing amounts of eradication.
But what's the reason for it? It's kind of a maintenance
for the stasis?
Yeah.
I mean, we're not really certain which components of the tumor don't get the drug as effectively. It seems that because the vessels on the exterior of the tumor are more active, we're able to get the majority of this amplification of drug delivery into those areas. So it may be that the core of the tumor is able to then relapse. But at higher doses, we do see increased prevalence of eradication, upwards of 50%. Thank you very much.